Okay, time to start chapter 4, Algebra in the Islamic World. Um, so let's start off with a little bit of an introduction, looking at kind of what was the state of algebra before it came to Islamic world and around the year 770, and what were the sources that these mathematicians used to really create algebra as kind of more like we know it. There's a big debate about, was algebra done by so and so? So let's have a look. So if we're looking for sources of really classical algebra problems that were an inspiration to these Islamic mathematicians, we can look at the Greeks, the classical Greeks, the Babylonians, and the Hindus in India. Okay, there were lots of kind of arithmetic problems, which we can think of as algebra, and also the Greeks were very, as we've seen, are really heavily invested into geometry, and that's how they did a lot of their algebra. So let's have a look. So if we're talking about Greeks and geometry, of course, we want to talk about Euclid. So sort of a classical kind of problem that the Greeks would consider, which we would think of as kind of like an algebra problem, would be to find some geometrical magnitude, whether a length, an area, angle, which is kind of related to the givens in the problem. You're given some known magnitudes, and then you're asked to sort of create some magnitude. Okay, so let's have a look at a really classical problem. This is Euclid Book 11 Book 2, Proposition 11. To cut a given straight line so that the rectangle contained by the whole and one of the segments equals the square on the remaining segment. So this is the problem of the golden section that we've seen beforehand. So it's asking, given a segment AB, find a point H on it so that AH, the square on that segment, AH squared, equals the rectangle, the area of the rectangle contained by the whole piece and the smaller piece. Okay, so let's kind of think of this as an algebra problem. So we want to find an x so we're given a is the length of our segment, and we want to cut it at x such that the rectangle on the whole times one of the segments, so let's say a minus x, is equal to the square on the other part. So a times a minus x equals x squared. So if we were to multiply this out and kind of respect the fact that they didn't like to use negative numbers, we would think of this as x squared plus ax equals a squared. And so we want to solve that. And so one way we could think about this, if we were trying to think of it as geometrically, is to try and have x squared and a squared as squares and ax as a rectangle. And that's what I've done in the little picture there. So the area in green, you can see x squared, and you can see above and by the side rectangles of area a over 2 times x, so ax over 2. So add that together, that's x squared plus ax. So that's the left-hand side of our equation. That's an area in green. And so that has to be a squared. That's our given. Now, the area in blue is a little square. It's a over 2 times a over 2. It's a squared over 4. So you notice here we're completing the square. So, completing the square is actually a geometrical thing. So that means big square that we have then has got side x plus a on 2. So that means x plus a on 2 squared equals a squared plus a squared on 4. So it equals 5a squared on 4. We take the square root. So we get x plus a on 2 equals a square root of 5 on 2. Notice we don't do plus or minus because we're doing geometry. All the lengths are positive. So we subtract a over 2 from both sides, and so we get x equals square root of 5 minus 1 on 2 times a. Okay, and so that's where you cut the segment to give the golden section. And right. Of course, that's not how Euclid actually did it, because if you go back and look at this, the way that I set it up there with that square, you know, I've sort of put in an unknown. I've actually sort of actualized it. And that's not how the Greeks would have wanted to do this. So the thing is, you're given a, b, and you want to find the point h such that you've got the golden section. So you've got to do a construction. It means you've got to start with a, b, and then you've got to do the things that we know that they like to do, things with straight edge and things with compass, to go ahead and actually cut that that segment AB. So you can't start off with what you're trying to prove. Okay, so this is in a sense how the Greeks maybe weren't doing 100% algebra that we would recognize as algebra. Anyway, so the procedure in proposition 11 by Euclid is given AB, you turn that into a square. You bisect a side AC at a point E, and you join it to that vertex E, so you get BE. And then you extend CA, and of course what you can do is you get your compass, you put it in the center at E, you put it on B, and then you can do a circle. And so that means you can then extend the side AC to F, such that EF has the same length as EB. After that, you turn FA up there into a square. And then that gives you your point H. And so the claim then that H is actually the golden section. We're not actually going to go through all the proof. The proof follows from Euclid 2.6, which Euclid 2.5 and 2.6 are going to turn out to be really important to us. They're the propositions that really give the justification for doing quadratic equations. But so what Euclid 2.6 says is the rectangle, which is CF by FG, together with the square on AE equals the square on EF. So that gives us something to start working with, and then we start working with the Pythagorean theorem, and you end up proving that you've got the golden section. Okay. So lots and lots of examples of doing quadratic stuff in the Greeks. Not much about doing stuff with cubics. In fact, I've only ever seen one, and that's from Archimedes, and that's from his famous book on the sphere and the cylinder. It's proposition 4. So what we do here is we take a sphere and we're going to cut it with a plane so that the volume of the two pieces of the sphere are to one another in a given ratio, like A to B. And so if we put this in modern terms, we get that expression here. We want to solve for x, so x is where you place the plane. So x can go from 0 on the south pole to 2r at the north pole. And you can see, like, if you plug in x equals 0, you get infinite. Now that's because all the stuff is in the top top portion, and if you let x equal 2r, then the plane is just at the top, so everything is in the bottom portion, so the ratio is 0. And Archimedes solved this by intersecting a parabola with a hyperbola. Okay, we've seen that kind of stuff before. Okay, so what do we think about this? So they're kind of doing algebra, but we don't really, it's not algebra that we kind of think of as algebra. So all Archimedes is doing here, and what Euclid did in the previous problem, is that they are constructing a length which solves the problem. They're finding something geometrical. Okay, whereas we are happier, like what I did in the first thing here. I'm doing something involving numbers. I'm getting an actual quantity as an answer, not a geometrical magnitude. Okay. The Greeks also did arithmetic, and this is really good arithmetic, Diophantus. It's really the birth of what we would call number theory. So someone's going to talk about Diophantus. Around 300, Diophantus wrote Arithmetica, and in this he gives lots and lots of problems, and then he solves the problems. Okay, so we've seen this, that mathematics is done rhetorically. It's all done with words. There's no formulas. So when you describe a situation, you can't just say, you know, the answer is minus b plus or minus square root of, or whatever. Okay, so here's an example of what I mean. So here's a nice problem from Diophantus. Find 3 numbers so that any product of 2 added to the third gives a square. Okay, very interesting problem. So Diophantus says assume the numbers are x, x plus 6, and 9. Okay, you're probably all going, what? Where does that come from? Well, let's just ignore that for the time being and see how that assumption helps us. So the squares need to be, you just go through the 3 possible combinations. So x times x plus 6 plus 9 is x squared plus 6x plus 9, and that's x plus 3 squared. So that's always going to be a square, so that's good. X times 9 is 9x plus x plus 6 is 10x plus 6. And then you can also do 9 times x plus 6, which is 9x plus 54. Add x, you get 10x plus 54. So they're the 3 numbers you want to be squared. And you see that straight away you've got 10x plus 6, 10x plus 54. You can just plug in x equals 1. And you'll get 64 and 16. And x plus 3, 1 plus 3 squared is 16. So you get squares. So plugging in x equals 1, we see that 1, 7, and 9 is a solution to our problem. Okay, so the start is pretty mysterious. Like, how can he just say x, x plus 6, and 9? So remember, he's not giving any formulas. He's just giving recipes, and he's giving hints about how you could solve this problem. So his hint is that choose with your numbers, you choose the numbers such that one of the conditions is always satisfied, right? We had in the first one, we had the x plus 3 squared. So we can see that our numbers were x times x plus 6 plus 9. So that way you have one definite number, and you see you only got 1 degree of freedom. Okay, so let's see what happens if we try a different perfect square. So let's try x squared plus 8x plus 16, which is x plus 4 squared. Okay, so if we start off with that, then our numbers are going to be x, x plus 8, and 16. Okay, so we do the x squared plus 8x plus 16, and that's x plus 4 squared, which we knew to do because that was the hint. Start off with a square. And then we've got 17x plus 8 and 17x plus 128. And now, well, the 17x plus 128 is not obvious how I can turn that into a perfect square. But the nice thing is, it's very tractable because you've got 17x in both those situations. So maybe we can subtract the 17x's away. So if we let one square be 17x plus 8 and another square be 17x plus 128, so I'll call one a squared and the other a plus b squared. Subtracting one from the other, we get 17x plus 128 minus 17x plus 8 is 120, and a plus b squared minus a squared is 2ab plus b squared, so we can factor out a b, so 120 equals b times 2a plus b. And so now all we've got to do, it's now a fairly straightforward problem. All we've got to do is choose numbers a and b such that 120 equals that. Well, I know, for example, that 6 goes into 120. Okay, so if b equals 6, that means 2a plus b has to be 20. So that means 2a has to be 14. So a is 7. So that's going to work. Okay, so let a equal 7. So that means 49 equals 17x plus 8. That means x equals 41 divided by 17. Okay, so 41. So if we let x be 41 on 17, x plus 8 is 177 on 17. That's my second number, and 16. That's another trio of numbers such that you take any two and multiply it and add the third, you're going to get perfect squares. Okay. Interesting. Okay. The Babylonians. So we've already seen that the Babylonians can handle quadratic problems. Like we saw one where a number was added to its reciprocal and it gives a given number. So what is the number that you started with? Or there are problems like given the sum and product of two numbers, find the two numbers. Or given the difference and product of two numbers, find the two numbers that you started with. Okay, so for example, if we look at something from Yale, here is this problem on a clay tablet. Given that the sum is 630 and the product is 730, how do we find the two numbers? Well, the scribe tells us that we halve 630 to get 315. We square that to get 1033.45. We then subtract 730 from that to get 345. The square root of that is 145. So one number is 315 plus 145 is 5. The other is 315 minus 145 is 130. Okay. Again, no formulas. There's just like showing by example how to do it, so that if you're given another problem like that, you just follow the same recipe. And we double check that things are right? Because 5 plus 130 is 630, and 5 times 130 is 730. So it is correct. And so what's happening here? So we've gotten the sum 630 and we've halved it. What do? We halve it, then we square it, and then we subtract the product, and then we take the square root of that. So it's pretty, if you analyze it a little bit, you see that the trick is this identity here. X plus y divided by 2 squared equals xy plus x minus y divided by 2 squared. Right? Hopefully you can see that, because x plus y squared is x squared plus 2xy plus y squared. And over here you get x squared minus 2x plus y squared. So the x squareds and y squareds are cancelling. So you've got to look at what the cross product here. On this side here, you're getting xy divided by 2 on the left-hand side. On the right-hand side, you get xy minus xy divided by 2. So both sides, you get xy divided by 2. And so if you just analyze the two things, you see, okay, you're given the sum, x plus y, you halve it, then you're squaring it, and that finishes the left-hand side. Then you subtract xy from the right-hand side, and then that's going to equal x minus 1 on 2 squared. So that means you take the square root. So all of a sudden you've got x plus y on 2, and you've got x minus 1 on 2. And if you add those two together, the y's cancel, right? You get x2 plus x2, you get x. And if you subtract them, the x on 2's cancel, and you get y2 minus y on 2. You get y. So you get back the original numbers, x and y. So you can just check that arithmetic. Another important source are the Sanskrit scholars working over in India. A very famous one is Brahmagupta. He was working in early 600s, and he wrote a famous work, the Brahmasphutta Siddhanta, which was dealing with astronomy, okay, but he had chapters on math. And in that, he included some really important algebraic concepts, like the rules for multiplying sign numbers, i.e. that plus times minus is minus, minus times minus is plus, and plus times plus is plus. He was really the first person that we know of that considered answers could be negative. Remember, at the same time, they're also including 0 in their numbers. And no, not actually as a number. They used it as a placeholder, but it's on the. It was the appearance of 0, very important. He showed how to solve these linear indeterminate equations, ax plus by equals c. So, right, you're given a, b, and c, and you want to find x and y. This turned out to be really important in their astronomy, because basically you just think of everything going around the Earth, everything's got a period, and so you want to figure out, well, when is the moon going to line up with the sun? When can you get an eclipse? Well, you've got to, how often the Earth moves, the sun moves, and the moon, and so that's how you get these linear congruences. And so he said that, if you have a particular solution to this, so once you find one solution to this problem, then you find them all, because the general solution is then going to be x equals p plus mb and y equals q minus ma, right, where m is any integer. And you can just see for yourself, right, because you just plug in p plus mb for x and q minus ma for y. You're going to get ap plus bq, and that equals c. But then what happens with the m's? You're going to get a times mb minus b times ma, and that's going to cancel out. He also explained how to find that particular solution, and it's got the best name of anything in this class we're teaching, the Kutaka, which means the pulverizer. So a little bit of Sanskrit for you. It's basically using the Euclidean algorithm for that. And he also worked on what we call Pell's equation, this x squared equals 1 plus py squared. one reason why this thing turns up, because if you find solutions to this, if you divide that equation by y squared, you see that you've got x on y squared is basically p. So this is a way to find a good approximation for square roots of numbers. So p is some non-square number. Later on, Bhaskar also kind of dealt with number theory problems. So here's a problem. What number, when divided by 3, gives a remainder of 2? When divided by 5, gives a remainder of 3? And when divided by 7, gives a remainder of 2? Okay, and so again, the solution is given. It's like an example, so that if you're given a similar problem, you can go back and you just follow the same method. So here's how Bhaskar solved it. Well, he said 70 is congruent mod 3 to 1, right? Because 70 equals 3 times something plus 1. So when we divide 70 by 3, we get a remainder of 1. And 70 is a multiple of 7 and 5. 21 is congruent to 1 mod 5. And 21 is a multiple of 3 and 7. And 15 is congruent to 1 mod 7, and 15 is a multiple of 3 and 5. Okay, and so he said, well, 2 times 70 plus 3 times 21 plus 2 times 15 is going to work. And that number is 233. And you can kind of see, right? Because if you divide that thing by 7, okay, it's going to divide the first, it's going to go into the 2 times 70, it's going to go into the 3 times 21. Into the 15, it's going to have a remainder of 1. So 1 times 2 is 2, and so you've got your remainder of 2. You do the same thing with 5. 5 goes into the 70, 5 goes into the 15, so you only have to worry about the 5 going into the 3 times 21. 5 goes into 21 with a remainder of 1. 1 times 3 is 3, and that's got the required remainder. So 233 works, and what you then do is just subtract off 3 times 5 times 7 until you get to the smallest number. So we subtract 210, and you get 23 as the answer. Okay, so it's not a formula, but it's pretty good. You can, given any similar kind of problem, you can now figure out the answer. Like if I change what the remainders are, you know how to change the example to get the right answer. Or if I give different remainders, different things to divide by, like if I want to divide by 11, I know how to go about doing that. Okay, so the Islamic mathematicians who started work on this in Baghdad in the House of Wisdom in the late 8th century, they had access to all these problems. So we know that there were Arabic translations of Euclid's Elements from the late 8th century. There were Arabic translations on the sphere and the cylinder from the early 9th century. There were Arabic translations of Arithmetica from the mid-9th century. Okay, so they had all access to all these Greek works, and they got these works, they translated, they did commentary on them, they worked on this, and they saw how there was an underlying algebra beneath this, and they kind of developed that more and more. When we looked at the history of the Islamic Empire around the 8th century, that's when they sort of conquered Persia and the Iraq region. And so they had access to all kind of like the Babylonian math from there. We know Sanskrit scholars came to Baghdad in 770, and their work was translated into Arabic by Al-Fasari. In particular, they translated Brahmagupta, and of course they brought along their number system. It should be noted that there was a little bit of problem in translating from Sanskrit to Arabic. So if Arabic is one of the great written languages, Sanskrit is probably one of the great oral languages. So I find this unbelievable. But a lot of the math was just memorized. The works would be memorized, and people would then just recite it. For example, and this included tables. And so what they would do, for example, they had tables of various values, like some sort of trig table. They would memorize it, and they wouldn't memorize the numbers. They'd have, it's like nonsense words. It's all based on what the syllables were, and they'd sort of memorize these syllable schemes, and that was how you memorized a table. So translating from the Sanskrit to the Arabic was considered, much more difficult than translating Greek into Arabic. Supposedly there was, difficulty with some words, and so when it came to translation, typically what I guess when you try to do a translation, you've got the words and you try and translate into their equivalent in that language. But what they would sometimes do is, they couldn't think of what that word meant, and so they basically just translated the sounds into syllables and into letters, like how it sounded, and so they'd write it down without giving it a really Arabic translation. And so this is sometimes how some words came into the language. And so, for example, we'll see that with the word for sign. So how sign got translated, it originally meant like bowstring, and by the time it gets translated into Latin, it gets translated as sinus, which means cavity. So we'll get that we'll talk about that when we get to talking about trig. So besides the actual works, from the Babylonians gave them the base 60 system, which we've seen is a good system for doing fractions in, and with the Babylonians had these good numerical procedures. From the Sanskrit scholars, they got their number system, which they then turned into later what became the Hindu-Arabic number system. We've seen that's really good for doing computations with. And the Greeks gave them geometrical rules to actually prove things. And so this is how sort of algebra, what we would consider to be real algebra, sort of came about. It was like blending the good numerical practices and procedures with the good geometrical procedures, which were good for proof. And so they could solve algebraic problems and also prove that their solutions were valid. And so this is what some people regard then as the start of the science of algebra. Okay, I'll stop there.